Okay, in the last video we talked about precipitation reactions. Now we're going to talk about acid-base neutralizations. It literally is the exact same process, the same 4 steps as is in the last video. The main difference is we don't get a solid at the end. So, the main concept with acid-base reactions is that anything that produces H plus is an acid, and those things dissolve in water. Anything that produces OH minus is a base. The idea is that these two things will react. It's essentially an O with 2 H's to become water. Okay, so instead of a solid, we get a liquid. It's no longer aqueous. This is the solvent. It can't dissolve in water because it is water. Otherwise, the process is exactly the same. So, let's try a couple examples. So, for example, if we have HCl, typical strong acid, and KOH, which is a typical strong base, we still do the same process. We figure out the charges first. H is in the first column, it's +1. Cl is -1, it's in column 7A. K is in the first column, and OH is one of the polyatomic ions, and altogether it is -1. Okay, we switch the negatives. So K and Cl are going to end up together, but H and OH are going to come together to make water. So I'm just going to write it as water. And then we end up with K with Cl. Okay, K was +1, Cl was -1. We don't need any subscripts right here. Now we do the aqueous solid liquid gas thing. Water is the liquid in this. We already know that. We don't even have to worry about the solubility rules. Anytime you see water in this, just leave it as liquid. KCl, K is always aqueous, Cl is usually aqueous. This thing is very definitely aqueous. And then the last step would be to balance this. Well, we have 1 Cl, 1 Cl, 1 K, 1 K, 2 H's, 2 H's, 1 O, 1 O. Everything's balanced. This one is particularly easy. I intentionally started with an easy one. But you'll see that it's the same process, but instead of getting a solid, instead of getting a precipitate, we get a liquid. Okay, let's try a few more. So this time we're going to use phosphoric acid plus sodium hydroxide. So our first step is to figure out charges. H's are +1. We have 3 of those, which works out nicely because phosphate is -3. Sodium is in the first column, so it's +1. OH is -1. And now we're going to switch the negatives. H and OH make water. We bring over 1 of each. I am fully aware this is H3, but we only need to bring 1 over here. This 3 is here because it's connected to something that's -3. It may not be over here. So 1 H and 1 OH makes water. And I'm just going to go ahead and preemptively label it as a liquid. Okay. And then Na and PO4. You always write the positive thing first, cation, then anion. Na has a +1 charge. Phosphate has a -3 charge, so we're going to need a 3 here to make the charges cancel out. Okay, so we have neutral salts, we've predicted our products. The next step is the aqueous solid part. Water is already taken care of, it's a liquid. This thing, we don't know anything about phosphates, but sodiums are always aqueous. Well, compounds with sodium as the cation are always aqueous. Okay, we have neutral salts, we have the solubility rules followed here. The last step is to balance this. Okay, I'm actually going to do the H's and O's last because there's O's in everything. I'm going to deal with the sodiums and the phosphates first. Phosphates, there's 1 here, 1 here. Sodiums, there's 3 here, 1 here. So I'm going to do 3 of those. Okay, I visualize H plus and OH makes water, so I see 3 H pluses and 3 OHs, so I need 3 waters. If that is confusing, you can also just balance the hydrogens. Okay, there would have been 3 here and 3 here, which is 6, and these are in packs of 2, so a 3 in the front would give you 6. If you double check everything, the oxygens are also balanced. We have 4 here, and another 3 here is 7. We have 4 here, and another 3 here is 7, so everything's balanced. Okay. And this is kind of the idea of how acids and bases work. The general trend is acid plus base yields some sort of salt that's usually aqueous and water. Okay? So if we look at any of these, that's acid, base, water, and salt. It doesn't really matter what order they're in, and then acid, base, water, and salt. Okay? It is possible for these to be solid, but they are typically aqueous. Okay? I need to explain an example of a weird base. We said in previous videos that bases are anything with OH minus as the anion. That is unfortunately too narrow of a definition for this. So we need to look at a couple examples. Okay. NH3 is an example of a weak base. So it does behave as a base, it's just not a great one. But you'll notice there is no OH in this. This is ammonia. Okay. The reason it is a base is because if you throw this in water, this essentially condenses down and becomes NH4OH, which now has OH as an anion. So it meets this definition. The problem is that occasionally you will see NH3 written like this on quizzes, exams, labs, and such. I need you to understand that it will become NH4OH, and you can honestly just write it as NH4OH and the rest of it follows the same rules and everything's fine. Okay. Another exception are carbonates. Okay, I guess I didn't write the word ammonia up here. Okay, these are also weak bases, and they're not super obvious as to why they are weak bases. They are weak bases because they react with H+. So up here, we saw that we're categorizing OH minus as a base because H+ is the acid, and it neutralizes it. You get water. Well, this also reacts with H+, but it's not an OH. Okay, it actually reacts with two equivalents of H+. So if you throw a CO3 2- in water, well, let's just do it this way. In the presence of acids, it will take two of those. This will be aqueous. This will be aqueous. What you'll end up with is H2CO3. This is actually an acid. This is called carbonic acid. It's really unstable. So if you were going to treat this like one of these problems and you had something like sodium carbonate, you would predict this product. If you switch the pluses and minuses, this is the answer you would get. The problem is this thing is unstable and you'll never find it. It immediately falls apart and becomes H2O liquid and CO2 gas. So you still end up with neutral solutions, and it does neutralize H+, and you end up with water, so we're going to treat it like a base. The problem is you also get carbon dioxide. Honestly, anytime you mix a carbonate with an acid, it starts bubbling. These are the bubbles, the CO2 gas. Okay, so let's try an example of one of those. Okay, let's try the ammonia one first. Honestly, if you just treat ammonia as a base, as NH4OH, because that's what it's going to turn into in water, if you write NH3 aqueous, this is essentially what you're implying here. We'll have that react with an acid, like H2SO4, and literally you just follow the same rules. This doesn't do anything exceptional. This is +1, this is -1, these are H+, this is -2. So we switch the negatives, and NH4 will go with SO4, and H and OH become water. So honestly, the NH4OH as a base is not really that weird. It doesn't do anything exceptional. So as far as balancing the rest, this is +, plus 1, this is minus 2. So we're going to need 2 NH4s to make that cancel out. Okay. Now we do the solubility rules. This one's a liquid because it's water. Ammonium compounds are always aqueous. Sulfates are usually aqueous. This will very definitely be aqueous no matter what. Okay. Now the last step is to balance this. We have 1 NH4 here, 2 NH4 here, 2 NH4s here, so I'm going to put a 2 here. 1 sulfate, 1 sulfate. Here we have 2 OHs and 2 H pluses, so this would be 2 waters. Okay. Let's try one with a carbonate. Okay. So let's say we have potassium carbonate, which dissolves in water, and we react, this is going to act as a base, we need an acid. Let's do HBr, pretty common acid. We're going to look at the charges. This is plus 1, this is minus 2, plus 1, minus 1. Okay, polyatomic ion, we should know that's that charge. We're going to bring one of everything over. So K with Br and H with CO3. Going to rewrite the charges. K is plus 1, Br is minus 1, H is plus 1, CO3 is minus 2. So we're going to need 2 of these. Okay. This is where things get a little weird. This is the one that we just saw on the previous page earlier in the video. This is unstable, and we can literally just rewrite it as H2O liquid and CO2 gas, because that's what it will turn into. We don't ever actually see this molecule. It's what you would have predicted by balancing everything out, but you need to be aware that anytime you see H2CO3, that it's going to break into these two things. Now, solubility rules. KBr, both of those things are always soluble. Well, Br is almost always soluble, but K is always soluble. And at this point, the only thing we have left to do is balance this. We have 2 Ks and 1 here, so we need a 2 in the front. We have a CO3 becomes this. I guess we'll just cross that out and worry about balancing this. 1C, 1C. Brs, we have 2 here, or sorry, 1 here and 2 here, so we need a 2 in the front. Now we have 2 H's, 2 H's, we have 3 O's, and we have 1, 2, 3. So this all balances out. But you'll note that anything with a carbonate is going to require this kind of extra step of visualizing H2CO3 as water and carbon dioxide. All right, thank you.